This video serves as a review for the students for the final in SPSS. What I have here is the infectious data that I will be using to do this review. You may have seen this data when we were reviewing the midterm. Um, as usually the case is when you have a data set, you would want to spend a little bit of time getting to know the data. So one thing you could do is look at how many observations or records you have by scrolling all the way down. So 137. The other thing you want to do is look at how many variables you have. So in this case, 55 variables. You may want to get a little bit of time to get to know the different variables. But for this exercise, I will just jump into the review. The first thing I will do is the independent t-test. An independent t-test is utilized when you want to compare the means of two groups. So the way we do it is we click on Analyze, then you go to Compare Means and Proportions, and then you're going to select Independent Sample t-test. In the test variables, you're going to select the variable that is the outcome variable. So let's say my variable of outcome is age, and I want to compare the age according to whether or not they've had abortion previously. So this is a previous abortion. So this data is about women health. Okay, so I'm going to put the second variable here. Usually you want to define your groups. You right click, you go to variable information, and then you can see what are the different codes used for abortion, 0 and 1. So you define your groups. This is going to pop out. You just have to specify that the groups are 0 and 1. Click continue. And I think for the independent t-test, that's it. You just go ahead and click OK. You're going to get two main tables. These are the ones that we want to focus on. The first table just says that according to abortion, yes or no, you're going to look at the age. So first you have 37 women that have had abortion previously, 99 did not have abortion previously. And then what you have here is the mean age for those that had abortion, 29.35, with a standard deviation of about 8 if I were to round. And for women who did not have an abortion, it's 27.7 with a standard deviation of 6.05. Then we move to the second table where you're going to actually have. So in this table, first thing we do is we look at the Levene's test for equality of variance. And basically this is telling us if we can assume that the variances are equal, or we may not assume that they're equal. That test produces F and a p-value, which is represented by the significance. So by looking at the significance, we can see that the significance is greater than the 5%, 0.05. Therefore, we fail to reject the null hypothesis stating that they are equal, meaning that we can assume the variances are equal. So we're going to read the first line. So as we go into the first line, this is the t-test, the degrees of freedom, but what really matter is the p-value. And we're going to look at the two-sided p-value, which comes out to be equal to 0.206. So that p-value is not statistically significant, and therefore we cannot conclude that these averages here indicate a statistical difference between those that had an abortion and did not have an abortion when it comes to age. Many times you will be lucky because the p-value, the two-sided p-value will be almost the same whether you assume equality of variance or not. But it's important that you realize which test you're going to use. So this is in a nutshell the independent t-test. If then let's move out to another test. I'm gonna go back to my set of data. I don't have to, but it's easier to start from here. This time we're going to do the pair t-test. Now the pair t-test is done when you're measuring something twice on the same people. I'm going to use the fasting blood sugar. If I look at variable view, here we are. We have two measurements of fasting blood sugar. One that is done at visit 1 and one is done at visit 2. So again, we're going to go to analyze, compare means and proportions, and you're going to down to paired t-test. In the paired t-test, you're going to identify the variables, the two variables of fasting blood sugar at visit 1 and fasting blood sugar at visit 2. And that's it. You just click OK. So here again, you're going to get summary descriptive statistics for fasting blood sugar at visit 1 and visit 2. The average fasting blood sugar for visit 1 was 81, with a standard deviation of 19.74. For visit 2, it was 96.5, with a standard deviation of 20.48. The second table is a correlation. We're not going to look at it. We're not interested in correlation. We're just going to move into the third table, which is the paired t-test. Here, there is no equality of variance needed. We just have to read the results. And what you get is the average difference between the two means. So the 81 minus the 96 produces a minus 15, the standard deviation of that. But what you're really interested is the two-sided p-value. It is less than 0.001, meaning that it's less than 5%. Thus, there is statistical significance. Hence, you will conclude that the difference in blood pressure the fasting blood sugar at visit 1 versus visit 2 the difference is statistically significant. The results are indicating an increase, a statistically significant increase in fasting blood sugar from visit 1 to visit 2. The third thing we're going to review here is a correlation. A correlation is typically done between two numerical variables, and I would like to know if there is a correlation between age and fasting blood sugar. So you're going to click on Analyze, you're going to go down to Correlate, you're going to pick the bivariate, and you're going to pick your two variables, age and fasting blood sugar at visit 1. And that's it. You just click OK. And what you're going to get is this table. It's a 2 by 2 table because we asked for two variables. So I have age and fasting blood sugar in rows, and also age and fasting blood sugar visit 1 in columns. Always the diagonal are going to produce a correlation of 1 because that's age with age, and fasting blood sugar with fasting blood sugar. The off diagonal are exactly the same because they're looking at the exact same thing. So the correlation we're looking at is between age and fasting blood sugar. It produced a correlation of 0.080. The p-value for that correlation is 0.354, not statistically significant. Hence, there is no correlation between age and fasting blood sugar at visit 1. As a reminder, a correlation is a value between -1 and +1. A value of 0 is indicative of no correlation. A value of +1 is indicative of very strong correlation, a one-to-one correlation, and a -1 is indicative of a very strong negative correlation. And as the values get close to 0, it means that the correlation is very weak. Next, I'm going to look at comparing between different groups, the mean, but this time not only two groups, more than two groups. For this analysis, we're going to have to use the ANOVA. All right, then we're gonna specify a few things. In the post hoc, we're going to request the Bonferroni. This is going to produce the Bonferroni adjusted p-value for multiple comparisons. And in the options, I've already selected them, but that's what you need to select: the descriptive, the homogeneity of the variance test, the Welsh, and the means plot. Click continue, and then OK. The first table you will see is the table that has the different groups. So if you remember, it's the method of delivery is either normal, C-section, abortion. The mean age for each of these three groups, and the standard deviation for each of these three groups. Then the next table is the homogeneity of variance. This is the equivalent of the Levene's test that we saw in the independent t-test. And in fact, you're going to see that you do have the Levene statistics. The one you're going to look at is based on mean, the first option right here. And then you're going to look at the p-value. Now, if the p-value is not significant, as the case here, then you're going to move into the ANOVA table and you will read the p-value of the ANOVA table, which comes to be 0.003 in our example. And this test, this ANOVA, is testing if there is a difference in the means between normal C-section abortion with regard to the age of the women. And the p-value is showing statistical significance, hence there is a difference between the three groups. If the homogeneity of variance turn out to be statistically significant, then the appropriate p-value to read would be the one of the robust test, the Welch. But in our case, as I said, since it is not statistically significant, the Levene's test is not significant, we read the ANOVA. Okay, now since the ANOVA is statistically significant, meaning that there is a difference between the groups when it comes to the age distribution, so the average age is different between the groups, and you want to know exactly where the difference is, then we move into the Bonferroni. And what the Bonferroni doing is comparing the normal delivery to C-section, and you'll read the p-value here, 0.04, meaning there is statistical significant difference between the age of women that had the normal delivery versus C-section. Then normal delivery versus abortion, and again, it's statistically significant. Then you're going to move into C-section versus normal. We already tested that previously. This is why if you look at the results from this row, the p-value is exactly the same as normal versus C-section from this row. Therefore, we're going to ignore this row and we're going to go to the next row, C-section versus abortion. And the p-value is not statistically significant, meaning there is no difference between C-section and abortion. The last two rows, we've already reached the conclusion regarding abortion versus normal and abortion versus C-section, hence there is no need to look at them. So these results are saying that the differences between those that had a normal delivery and C-section, those that had normal delivery versus abortion. And therefore, the last thing we requested was the plot. And you can see that the age for the woman that had a normal plot was the lowest. Then comes the C-section, then comes the abortion. And our results indicated that normal was statistically different from C-section, statistically different from abortion, but there is no difference between C-section and abortion. So this ANOVA that we ran now is equivalent to the independent t-test because the groups were independent. The next analysis we were going to do is what if I have an ANOVA, however, it's the same individuals. So what is the equivalent of the paired t-test but using ANOVA? For that setup, you're going to have to go to analysis and you're going to have to go for the general linear model and you're going to pick the repeated measures. First thing you're going to do is you're going to name the variable that you're comparing. So I'm going to back up a little bit just to let you know what variable I'm going to look at. The variable I'm going to look at is the child's body fat, percent body fat. So each of these women participating in the study had 4 children before the current pregnancy, and every child was measured for body fat percentage. So we are wondering if there is difference in body fat, whether the child was the first born or second born or third born or fourth born. But these children are all siblings, so they're all belonging to the same mother. Hence, there is the paired data, pairing by the fact that they are siblings, pairing by the fact that they were born to the same woman. So we have 4 children, and we're comparing them with regard to their body fat, percent body fat. So we're going to go to analyze general linear model, repeated measures. SPSS automatically gives the name, which is factor 1. It's much better if we change it to the actual variable. So I'm going to call it body fat so that I remember what I'm looking at. There are 4 children, so the level is 4. Click add, and then you move into define. Now, you told SPSS that you have 4 variables that are measured on the same individual or the same mother here, because these children belong to the same mother. You have to tell SPSS which are these variables, so it happens that they are at the end, so that makes it easier for me to find them and to put them in the in this section here, which is the within subject variables. Next, we're going to request a few things. First, I'm going to the post hoc. No, I'm sorry. I'm going to the EM means, meaning estimated marginal means. I'm going to request that the body fat shows to be shown the display mean for the body fat. I want a Bonferroni correction, therefore I'm going to click on the compare and I'm going to select the Bonferroni. Then the next thing I'm going to do is the the options. And under the options, I'm just going to go with the descriptive statistics. The last thing is the plots. And I will request that the plots, the body fat would be shown on the horizontal axis. Have to click add and continue. And I think we've selected everything needed for this analysis. Click OK. All right, so first thing is the names of the 4 variables that you chose. Next, descriptive statistics, hence it's showing us that the first child had an average body fat of 17.7% with a standard deviation of 5.7. The second child, it was 17.7, very similar to the first one with a standard deviation of 7.54. The third child, what was about 15% with a standard deviation of 8. Last child, 15.6 with a standard deviation of 9. The next table is the multivariate test. We're not going to look at it. We're going to jump into the test of sphericity, which is the equivalent of testing the equality of variance, but for repeated measures. And here what you need to do is to look at the test, the W, the Mockley's test, and what matters is the p-value. It is statistically significant, hence we cannot assume sphericity, and that is going to be relevant when we come to the next table. This is the ANOVA table for our repeated measure analysis. You see that you have multiple rows, the sphericity assumed, and the 3 others all correct for not being able to assume sphericity. The one that we're going to pick is the greenhouse geyser. So by reading the greenhouse geyser, the p-value, which is right here, significance is 0.003, statistically significant, indicating that the percent body fat for child 1, child 2, child 3, child 4 are not equal, and there's statistical significance between these children. Now, I want to know more about this. So next is the test of within subject. We're going to ignore that. We're going to ignore this table. This table is the estimated marginal means, which we requested. It will give you the same means that we had previously with a standard error instead of standard deviation. So again, we're going to skip that, and we're going to jump into the Bonferroni pairwise comparison right there. So the way to read this is that this is the first child compared to the second child, and the p-value is 1, so no statistical difference between child 1 and child 2. Child 1 versus child 3, the p-value is 0.007, statistically significant. And child 1 versus child 4, the p-value is 0.154. So far, child 1 is only statistically different from child 2. You come to child 2. Child 2 compared to child 1, we already compared that, so there's no need to look at it. We're going to look at child 2 versus child 3, and there is statistical significance. Child 2 versus child 4, no statistical significance. So again, child 2 is only statistically different from child 3. You come to child 3 versus child 1, we already compared that. Versus child 2, we already looked at that. We only need to look at child 3 versus child 4, and there's no statistical significance. Child 4, this is redundant because we already compared child 4 to all previous children. So overall, the conclusion is that the difference really is between child 1 and child 3 and child 2 and child 3. This is further illustrated in the plot that we requested. You can see that child 3 is way down here, whereas child 1 and child 2 are way up there. So these two are statistically different from child 3, but the difference is not quite large for child 4 to be statistically different from child 1 and child 2. So based on our analysis, only child 3 is different from 1 and 2, and that's it. That's the only difference. All right, so that concludes everything we needed to talk about for comparing means and correlation. We're only left with comparison of proportions. I'm gonna go back to my data, and the variables I'm gonna use this time is whether the woman had a history of chronic disease, which is this variable right here, versus the result of her OGTT results. So whether she had an OGTT result and whether it was, if it was done or not done, basically. Okay. All right, so we're gonna have to go to analyze descriptive statistics, and we're going to go to cross tabs. The groups I would like to compare, I put them in the column, and I think we wanted to compare whether the women had a history of a chronic disease versus not having a history of chronic disease, which is this variable right here. Put it in the column. And the proportion I want to look within these two groups are whether or not the OGTT was done. So that's the variables. I put it in the rows. In statistics, I'm going to request the chi-square analysis. If I do not meet certain requirement, I would require I would require under the exact, the option, the exact right here, but let's wait for that. So let me back up. Again, what I did is I clicked on statistics and I requested the chi-square. Then in the cells, what we're going to do is we're going to create style using APA style, and we're going to request a Bonferroni corrected p-values for pairwise comparison. Okay, and we're ready to run the analysis. All right. So if you remember, what this is going to produce is a table that has whether the women had a chronic disease, no or yes. So the total that had chronic disease is 18, and 118 did not have chronic disease. And then either the woman did not do the OGTT, or she did, or it was not even recommended. Okay, and you see that the percentages produced are within the column. So the percentage, if the woman did not have chronic disease, about 11.9% did not do the OGTT, 50% did the OGTT, and 38.1% it wasn't even recommended. If you look to the women that had a history of chronic disease, 33.3% did not do the test, 22.2% did the test, and 44.4% it wasn't even recommended. Now, to know if there is statistical significance, we come to the chi-square table. First, you start off with checking the requirement. So in the footnote, you look at the percentages between the parentheses. And as I told you, the percent has to be below 25%. Here it is less than 16.7, so it is fine. We can use the Pearson chi-square. Had this percentage been larger than 25%, you would have to request the exact option that we requested that I showed you a minute ago. But here we're fortunate so that there is no need to request the exact. We can go ahead and read the results. So the p-value is 0.022. There is statistical significance. Obviously, there's a difference in the proportion between women that have a history versus women that do not have a history of chronic disease. But the question becomes, so the difference is between where the difference lies. And the answer is by looking at the subscript letters. This is the Bonferroni comparing percentages. You can see that for the no, there is a little a here and a little b here, meaning that these two percentages are statistically different. For those that actually did the OGTT, the letter A for among no chronic history diseases versus the yes, there is a letter B. Again, these two percentages are statistically significant. And when it comes to if it was not even recommended, then it's a letter A and a letter A, meaning there is no difference. So the way to interpret these results, there is a difference in proportions of doing the OGTT between women that had a history versus women that did not have a history of chronic disease. The difference does not come from whether or not the test was recommended because the percentages are the same. The difference comes whether or not they did the test. And what we're seeing is that if a woman had a history of chronic disease, there is a higher percentage of her actually not doing the test, 33% versus 12%. So that's where the statistical difference is coming. Similarly, there is a lower percent among these women to doing the test versus if she did not have the chronic disease, the 50% versus the 22%. So this is basically in a nutshell everything we talked about. The one thing that remain and that we did not address is the equivalent of the paired t-test or the paired ANOVA for the chi-square. And that's where if you go to analyze and you're doing the crosstab, so maybe you will have, let's say, OGTT first time, OGTT the second time, and then in the statistics, you're going to request the McNamara test. And that is the test that you will have to read, not the chi-square tests. All right, I hope you find this review session helpful.